All right, welcome back, everybody. So we are now actually in the final material lecture of the course. So we are going to start today. We'll finish next week. Then we'll have a wrap up in the next week. But basically, this is the last course unit that actually contains material. This is going to be a high-level unit. Why? Because I'm just going to introduce a language just like SQL that is just as high-level and easy to use as SQL, except that that language also supports data when it's nested and heterogeneous. So in document stores, you notice that this is kind of low level, right? This language, even though we can deal with nestedness and heterogeneity, that language is low level. But you see the progress we've made though, right? We have this whole stack. We have storage, HDFS or S3. We have syntax, XML or JSON. We can have 3 data models, that is denormalized tables. We can validate our data. We can fit it in DataFrames. We can process with Spark. We can build indices in the case of MongoDB if you have an ETL system, hash indices, B+3 indices. We have data stores like MongoDB and so on. And now the ultimate level, because user interfaces are not part of the lecture, is the querying language. How does that work on a high level? Well, it's this data independence idea that we have at the logical level a language like SQL, and physically, I might have PostgreSQL, IBM, Oracle, Microsoft, or whatever system that I have, but the language is the same. It's just SQL, right? And I don't care about the details. In fact, we saw that SQL runs on top of Apache Spark, for example, with Spark SQL. It also runs on top of HBase through Hive. It runs on Apache Spark, as I said, with Spark SQL, and that can actually be compiled internally by Spark to actual transformations. But do you prefer this or do you prefer this? I'm pretty sure this is the part that you prefer to write as a data scientist, right? Because this is more cumbersome to write. The benefit of a high-level language is that this is what you type in your Jupyter notebook, right? So of course, there are also the Spark SQL transformations, but nevertheless, it remains easier to type something like this. And for the people who really, they love to program and so on, you can still also put your SQL in there inside a SQL command, right? But with the magics in Jupyter notebooks, it's possible to only have to type that. However, SQL works great if the data is homogeneous, normalized. You have your columns, it's always the same types. It's in first normal form and so on and so on. This is where SQL shines. In real life, and this is what we saw with big data, the data is not going to be flat and homogeneous. You're going to have extra values, missing values, invalid values, nested values, tables in tables, and so on. This is the whole JSON and XML part, right? SQL is not good for that. And the way we saw that it's not good for that is that when you have data frames and you try to fit a data set that might be not very clean, right? Here you have an object, here for the same field you have a string, then you end up dealing with low-level considerations in order to distinguish between this and this, right? This is very complex. As a data scientist, having to deal with that is really not something you want. Moreover, it can very quickly become complicated to actually use SQL to query arrays. Right, you see, like this is really, really cumbersome to write lateral view and so on and so on. So very quickly you reach the limits of the whole thing. And you end up writing like absolutely gigantic queries sometimes, because SQL was not designed for nested data. It was designed for tables. The good news is that there is a new generation of languages. They look a little bit like each other and use the same ideas that can do that you would do in SQL with that amount of code. And the reason is these languages are actually designed for data that is nested and heterogeneous. So that's the reason why they are more compact and easier to use, right? And the language we are going to learn in this lecture is called JSONic, right? So JSONic looks like this. You will see that it has a lot in common with SQL. A lot of the ideas and constructs are going to be similar to SQL. It also has the relational algebra and so on and so on, but it's just a little bit more flexible, right? I was actually involved in the development of JSONic. It was something that came up as part of the standardization of a language called XQuery, that is used for querying XML data. The goal of JSONic was to bring it to the JSON side because JSON is gaining in popularity. So JSONic is actually easier than XQuery to learn because it focuses on the JSON data model. All right, but you will see there's plenty of other languages. But if you know JSONic, it will be very easy to learn any other language you want. A typical data set that we like to use, including at the exam, I think it's been quite a few times at the exam, is the GitHub archive data set. In total, of course, we don't give that all to you at the exam, right? But it's a few terabytes of data. It's nice because it's nested, so it has a lot of nestedness in there. Plus, it's heterogeneous because if you look at the path, 10% of the time you have mixed types, meaning that the same location might be an integer in that object, a string in that other object, or an array in another object. And that happens 10% of the time. There is no way you fit that in a table, except by hitting it with a hammer and, and having the issues that I described with DataFrames. And moreover, there's a lot of extra attributes because every object here has less than 100 keys. Attribute is a JSON key. It's called attribute in the context of DataFrames or tables. So every object has less than 100, but if you look at the unique attributes over the entire collection, there's more than 1,000. So this here is already beyond what a relational database can do. Typically, a relational database can deal with 255, 266 attributes, but not more than that. So you are beyond what a relational database can do and what SQL can do. And the idea is that just like SQL is a high-level way of interacting with tables, JSONic is a high-level way of interacting with nested and heterogeneous data. And just like SQL, it's data independent, meaning you have a language there. It can run on Spark, on Hadoop, could be also implemented on HBase, and so on and so on. Well, actually, it is because Spark can query HBase. Technically, you can actually use it on HBase. And a specific implementation of that, of JSONic running on top of this, was developed right here at ETH. It was done by some of your colleagues, students in master's thesis, master's thesis, and so on. And that's called RumbleDB. So there is a mandatory reading material that is the RumbleDB paper that I recommend that you read that explains that on the high level. It's a working implementation. We've been using it in teaching for a long time. We also use it at the exam now. And you can use it also in the future if you have projects and you need a high-level way of querying data. It uses Spark actually internally. But the nice thing is that you don't even need to talk to Spark at all because all you need to do is write JSON. All right. So what characterizes JSONic is that it's a query language. And as a query language, it is declarative and functional. That is what makes it different from JavaScript or Python or Java and so on. So for a declarative language, you say what you want, just like SQL. You don't say how. You don't actually care how. You just say what you want. And the idea of a functional, so this is declarative language, you say what you want. A functional language is like a Lego game. You just manipulate data and every construct of the language takes data in and puts data out. Right? So it's like a big Lego game with expressions that where the data flows, just like the transformations in Spark actually, but on a higher level. And you pick an instance of the data model that would be a collection of trees, and you output a collection of trees. Right? And finally, unlike Java or Python and so on, you can manipulate more than one record at a time. You can manipulate a whole table or a whole collection of trees. So it means that whenever you output something that can be a collection of 1 billion of items that you output right there. So it's really just like a Lego game. That's really how to think of that language. And you can mix and mix and mix the expressions in plenty of ways as you want. More concretely, and this is what I'm going to show you before we go get some lunch, it's really a data calculator, right? Think of it that way. If you have a calculator, you can do 1 + 1 gives you 2, 3 + 2 × 4 gives you 11, just manipulates numbers in that case, right? 2 > 5 gives you true. You can have let, just like in functional language, let $i = 2 return I + 1, that gives you 3. But look, this is the beauty of it. it doesn't just do numbers, it also does arrays and objects. So here you have an array, it just outputs itself, just like if you put 1, you get 1 out, right? So the array outputs itself, just like JSON. An object also outputs itself. If you say object.foo, and here that's really just like, instead of numbers and plus, we use objects and dots, but foo1.foo gives you 1, because the .foo navigates to the 1. If you have an array, this double square bracket takes the position 1, and we start at 1, so it gives 3. Position 1 gets you 3. Now, more complex, you just compose, just like you do with numbers, right? This is a JSON object that associates foo with an array. .foo extracts the array. The square brackets 1 extract that value, so you get 3. And then you do plus 3, 6. So that's really literally a calculator, but with data. Another one, I have an object foo associated with an array. .foo gets the array. If I use the square brackets, it opens the array. So now I have my 3, 4, 5 in the wild, right? Because as I said, it's collections of items. So now I have a collection of 3 items, 3, 4, and 5. So it's a calculator that is that can return multiple values. Actually, it can return billions of them. You also have this 1, 2, 4 that outputs a string like that.
Oh, we have a question. How is it different from Python?
Okay, so I will answer, and that will be the where we stop today. It's different from Python because Python is an imperative language. Python is an imperative language, like Java or C++ and so on. JSONic, like SQL, is a functional and declarative language. That's the difference. In JSONic, you don't have variable assignments, you don't have while loops, you cannot modify variables and so on and so on. Python is not a calculator because you can actually modify, well, it's a different kind of calculator where you can modify values. But JSONic is really functional and declarative. That's the idea. So it's closer to SQL than it is to Python. But it might feel like Python in terms of ease of use, right? But it has this subtle difference. Does it make any sense?
But I saw a loop.
Oh, the for loop. We'll discuss it next week. It's not a for loop in the same sense of Python. We will look into that next week. It's not, there is no order in the for loop, basically. That's the difference. It's really like a select from where. If you see a for in JSONic, think of it as a select from where. That's pretty much what it is, right? Okay, so I suggest we stop here. And of course, next week, we are going to explore more the language, and I'm going to give you a tutorial and so on. We'll dive into the details of the language. That was just the appetizer. All right. So thank you very much for being here, also on Zoom. And I just see you next week at the same time for the continuation of the lecture. Thank you very much.